Hi friends, welcome to Civil Learning Library for the topic tension members on steel structures. See, tension member is also a structural element which carries only axial force. The entire cross section of the tension member is carrying uniform stresses. A member in pure tension can be stressed beyond the yield limit and does not buckle locally or overall. The best example is tension rod. Here some of the pictures represents for the tension members. This is the tension rod. This is wires or cables. Then angle, and then this is a channel, single channel, double channel, T section, then flat bars or rectangular section, then this is a box section, then I section, and this is some of the images for the truss. You can see this truss, and just this arrow indicates the tension member location. And if you see this portal frame, this brace located as a tension member, and you can see this bridge also. This vertical rod will be considered as a tension member based on the load path. Next, this some images placed here for the tension members. For this is for a roof truss. This ties will act as a tension member. This suspenders, this vertical will act as a tension member. Here, this sag rod will act as a tension member, and for the suspensor bridges, this stay cables will act as a tension member. And for a building, this X bracing in roof or wall, it will act as a tension member images. Next, we will see the limiting condition for the tension member design. First one is tensile yielding. Tensile yielding generally will occur at the mid part of the member, and excessive deformation will happen due to the yielding of the particular member cross section. Here I am taking example of one flat bar, and this is the tensile yielding location at mid portion of the flat bar. This both end, there is a connection will be there in this flat bar. So generally tensile yielding will start at this portion. You can see this image. So this is some image representation of tensile yielding. So to avoid tensile yielding of this particular plate, we have to design the plate as the yield strength of the plate should be higher than the stress at cross sectional area. So we know that the formula is P by A. P is nothing but the acting load, and A is the this cross sectional area of this particular plate. It should be lesser than the yield strength of the plate. And here we can use the factor of safety. For LRFD conditions, we have to use 0.9, and for ASD conditions, we have to use 1.67. Next one is tensile rupture. Tensile rupture is nothing but tensile yielding, but the applied forces are compared against the rupture strength in the region of reduced effective section. It means we have to compare with the net area instead of gross area. Generally, the net area will be reduced due to the presence of holes in the particular location of the connection. So the applied forces should be checked for this net area. So to avoid the tensile rupture, we have to check the plate. Ultimate strength of the plate should be higher than the stress at net sectional area. So here the stress should be lesser than the ultimate strength of the plate. For the tensile yielding, we are checking with the yield strength of the plate. So that is the only difference. There is a yield and ultimate capacity. So here the formula is Fu into AE, and AE is nothing but the net effective area. So this net effective area we have to calculate using the formula AN into U. So here this U is shear lag factor. This shear lag factor we can get it from this table from AAC. While doing the calculation example, we will see detail about this choosing of U lag factor from this table. And factor of safety for LRFD is 0.75 and for ASD is 2. Here you can see the image representation for the tensile rupture. It will happen mainly at this connection location where the forces are transferred. So it will happen like this due to tensile rupture, this fractures and all. Third limitation is slenderness. Based on the AIC 360, actually there is no maximum slenderness limit for the some tension members like rods or hangers. But if you are designing the member as a tension, the maximum slenderness ratio L by R preferably should not exceed 300. But this value is not applicable for rods or some hangers in tension. So here the R is nothing but the least radius of gyration, which is square root of I by A. And also we have to check some other limiting conditions for tension members. based on the particular connections. So that are listed here: block shear rupture or shear yielding or rupture, then net area, effective area, bearing checks. So these checks and all we have to do while doing the tension member design based on the connection type. Next week, actually, we are uploading part 2. In that one, we will see the design examples for the tension members like pin connected members, eye bars, rods, some kind of bracings in that presentation. Thank you for watching the presentation. Please subscribe for more videos and updation.